Alright, Algebra 2 students, this is lesson 1.7, solving absolute value equations and inequalities. So put a date on, and let's begin. So let's start with the definition. The absolute value of a number is the distance the number is from the origin, of course origin is just 0, on a number line. And so, if I write it like this, with these vertical bars with an x in the middle, this means the absolute value of x. That's how we read that. And one thing to keep in mind is that distance is always positive. So therefore, the absolute value of a number will always be positive. So let's take a look at that down below here on our example number line. So I'm going to number this from -4 all the way up through 4. And for one example, I might say the absolute value of 4 is equal to 4. And that makes sense because, again, this is really saying the distance of 4 from the origin, or 0, is equal to 4 units. And that makes sense because we can see from 0 to 4 is going to be 4 units, or a distance of 4. By the same token, I could say the absolute value of -3 is equal to 3. This makes sense because, again, the distance from the origin, 0, to -3 is going to be a distance of 3. Again, it's always positive. So this is telling me what the actual distance is. This is telling me what I'm taking the distance for. Finally, the absolute value of 0 equals 0, and this makes sense because 0 is right at itself, and therefore there is no distance at all to get from 0 to the origin because we're already there. Let's talk about absolute value equations. So most absolute value equations have two possible solutions. And we say most because that's not true for all of them. We'll look at some of those examples, but for most of them, if we have the absolute value of some number x and it's equal to another number a, then x is going to be either equal to a or equal to the negative of a. And let's take a look as to why that might be true. So let's take a look at this example. The absolute value of x equals 7. Now I want you to imagine for a minute what numbers can make this value of x true. And we can look at this by erasing the x for a minute. So the question is, what would I put inside this absolute value in order to make this equation true? Well, I know that one possibility is I could simply put 7 in there because the absolute value of 7 is 7, right? I could also put -7 in there. That would work as well because the absolute value of a number is always a positive. Keep in mind, however, what was originally inside there was x. And because the only two numbers that can work in there are 7 or -7, that must mean that x is equal to 7, or alternately, x must be equal to -7. These are the only two possible things that make the equation true, and we can see that that's true by simply plugging each of these back in for x again. On a separate example, or a second example, if I have the absolute value of y equals -5, I want to go through that same procedure and say, okay, well, if I erase the y here, what could I put in there that would make this true? This one's a little different though, because if I put 5 in here, the absolute value of 5 is 5. It's not -5. So 5 doesn't really work. If I try -5 in there, the absolute value of -5 is still equal to 5, and therefore still not equal to the -5. So in this case, we're going to have a different answer. Because there are no values of y that will make this true because the absolute value can never produce a negative, I'm going to say that there are no solutions to this equation. And another way to express that would be by showing an empty set. And this is the symbol for empty set. And we'll talk about solution sets in just a minute. Okay? So either one or the other of these would be fine. We don't need both. They mean the same thing. All right, let's talk about a method for solving absolute value equations. Our first step is to isolate the absolute value on one side of the equation. So we need to get the absolute value all by itself. Once we've done that, as we sort of had here where the absolute value was all by itself on one side of the equation, then we'll be able to use our definition of absolute value and use some logic to write the two possible equations, just as we did here and here, right? So we said the two possible things that x could be would be either 7 or -7 if in fact the absolute value of x equals 7. Our next step, one other thing to remember on this is that notice that we did not write the absolute value on these equations. So it would not have made any sense in my example up here to put an absolute value here, because of course this is exactly the same as that, so I haven't really gotten anywhere. And this, as we saw from our example over here, has no solutions. So basically I've said I don't have any solutions here, and this is no different. So I've just written the same thing again. Okay, so we leave off the absolute value symbols when we break our equation into the two pieces. All right, now we're ready for step number 3. And for step number 3, it says we're going to solve each equation. And so solve each one separately. In the one of our example there, of course, there was nothing to solve for x is already by itself. And then finally, we want to check the solution. And this is really important because there are times where we will have extraneous solutions, or solutions that appear to be solutions when we solve the equation, but when we plug them back in, they don't actually work. Not because we made a mistake, but because they were an extra solution generated by our procedure or our method. So checking here is not optional. We really need to do this to make sure that we're not getting fooled by an extraneous solution. So once we've checked our solutions, we're going to discard the extraneous solutions and then write the final answer in a solution set. And the reason why I want to do this, putting the answer in a solution set, is to really indicate that these are the final answers as opposed to the possible solutions that we found earlier. Braces, of course, are just the way that we indicate a set, and a set is just a group of numbers. In this case, our solution set is our set of solutions, and the braces are just like this. So that's opening the brace and closing the brace, and that just indicates a set of numbers. All right, let's take a look at some examples. So here it asks us to solve each absolute value equation. And our first step, as we saw from before, is to isolate the absolute value. Well, in this case, the absolute value is already on one side of the equation by itself. It's the absolute value of 2 minus 4x equals 15. So that part has been done for us. Our second step is to find our two possible solutions. Again, if I were to briefly obscure what's here in the middle and think about what my two possible solutions are, I can see that either a negative 15 would make this true, or a positive 15 would make this true. And therefore, whatever is actually inside here could be equal to either positive 15 or negative 15. Of course, what's inside there is 2 minus 4x. And so that leaves us with our equation, 2 minus 4x could be equal to 15, or 2 minus 4x could be equal to negative 15. All right, so those are our two possibilities. Now, notice we don't have absolute value on these, right? We talked about this. We don't leave those on, right? The whole idea of breaking into these two pieces is to allow us to get rid of the absolute value. And so now I'm ready to go ahead and work through solving each one of these inequalities. So on my first equation here, if I subtract 2 from both sides, that'll give me negative 4x equals a positive 13. And then dividing by negative 4, in both cases, will give x equals negative 13/4. I'm just going to leave it like that for now. Going over to my other side, subtracting 2 from both sides will give me negative 4x equals a negative 17, because I'm subtracting 2 from a negative 15, and then dividing by negative 4 will provide x equals a positive 17/4. Now those appear to be my two solutions, but I need to check both of them. So here's my check. So I have the absolute value of 2 minus 4 times the value that I found, negative 13/4. Close absolute value equals 15. Working that down a bit, I can see that if I put the 4 over 1, the 4 and the 4 cancels, even with 1 and 1. And so I'm left with the absolute value of 2 plus 13, because there is a negative times a negative here. So plus 13. Keep in mind this is not 12 at absolute value, so make that a little bit larger. Equals 15, or finally I find the absolute value of 15 equals 15. And that is in fact true. On my other side, I'll have the absolute value of 2 minus 4 times 17/4, close absolute value, equals 15. Again, notice I'm going back to my original equation. There is no negative 15 here because that's not what was in my original equation. Again, I'm going to put the 4 over 1, canceling the 4's. And that'll leave me with 2 minus 17. The absolute value of that equals 15. And simplifying inside my absolute value, I get negative 15, or the absolute value of negative 15 equals 15, which of course is true again. The absolute value of negative 15 is equal to 15 because it's just the distance of negative 15 from the origin. So now I'm ready for my solution set. And my solution set in this case will include both of my solutions. And so, therefore, negative 13/4 is one solution, and 17/4 is the other. And that's what I'm going to box as my final answer. All right, let's go ahead on to our next one, number 2. And again, our first step is going to be isolate our absolute value. So in this case, I need to move the negative 11 to the other side in order to isolate the absolute value. That will provide me with the absolute value of 5x plus 6 equals negative 9. All right, the absolute value is by itself. Our next step is to break this into the two possible equations, if there are such. And so, again, we're going to take a look at what happens, what can I put inside my absolute value here, here and here, in order to make this equation true. And I can do that by just briefly erasing my middle part and think about, okay, what numbers can I put in here? Well, if I try to put 9 in, the absolute value of 9 is not equal to negative 9. It doesn't work, right? Because, of course, absolute value is positive. If I try negative 9, the absolute value of negative 9 is also equal to positive 9. So that doesn't work either. Which means in this case, it's like we saw in that previous page, where I cannot have an absolute value that's equal to a negative number. And so therefore, I know that here, no matter how complicated this is, because there's nothing that I can put in here in place of this to make this equation true, then this is simply going to be a no solution problem. And so my set won't have anything in it, my solution set won't have anything in it, so I can just put empty set. Or I could write no solution. Let's try another one. Now this one you might be tempted, number 3, you might be tempted to write this off as a no solution as well. Because look, there's a negative on this side. Here's the thing to keep in mind though. I still have a 5 here and a negative 3 that I haven't gotten away from my absolute value. And I need to do that first before I start jumping to conclusions about whether or not there's going to be possible solutions here. So therefore, I need to isolate my absolute value first. I can do this by first subtracting the negative 5, or subtracting the 5 rather. So absolute value, or negative 3 times the absolute value of 2y plus 2, closed absolute value equals negative 12. I still have a negative 3 here, so I'm going to divide both sides by negative 3, causing the negative 3 that's on the outside there to cancel, and so I'm left with absolute value of 2y plus 2 is equal to positive 4. Alright, now I can see that there are some possible solutions here, right? Because 4 is positive. And I know that the two things that I could put in place here is either negative 4, the absolute value of that will be equal to 4, or positive 4, the absolute value of that is equal to 4. So therefore my two possible solutions here are 2y plus 2 could be equal to 4, or 2y plus 2 is equal to negative 4. For my first equation, I'll subtract 2 from each side, giving me 2y equals 2, and then dividing by 2 will provide y equals 1. My other possibility is when I subtract 2 from both sides for my other equation, that will provide 2y equals negative 6, dividing by 2 equals negative 3. So those are my two possible solutions. Now I'm ready to go back and check. And again, I'm going to plug back into my original equation. So I'm going to have 5 minus 3 times the absolute value of 2. One of my answers was 1, so 2 times 1 plus 2 equals negative 7. Working that down a bit more, I'll have 5 minus 3 times the absolute value of 2 plus 2 equals negative 7. And then 5 times negative 3, or sorry, 5 minus negative 3 times the absolute value of negative 4, checking to see if that is negative 7. And then finally, because the absolute value of 4 is simply 4, it'll be 3 times 4, and therefore 12. And I can see that that is in fact true. Negative 7 is equal to negative 7. So I have one possible solution, which is this one. This one works. Now I want to check my other one. So here I'll have, again, 5 minus 3 times 2 times negative 3 plus 2, closing the absolute value, and we're checking to see if that's equal to negative 7. Working that down, I'll have 5 minus 3 times negative 6 plus 2, seeing if that's negative 7. Going a bit further, I'll have 5 minus 3 times the absolute value of negative 4 equals negative 7. Now it might be tempting here to think that this is going to become a positive 12, right? But it's not, because I need to do the absolute value first. Absolute value is a grouping symbol. And so the negative 3 hasn't changed, but the absolute value of negative 4 really becomes a positive 4. And therefore I'll end up with 5 minus 12 equals negative 7, which of course we can see is true. So therefore I can write my solution set. In this case, my solution set will be 1 and negative 3. So both of those solutions worked. All right, let's take a look at number 4 together. So in this case, again, I need to start by isolating my absolute value. And the thing hanging out with my absolute values is 1/2. And so I'm going to deal with that by multiplying both sides by 2. Now, of course, when I multiply the other side by 2, I need to distribute it to both pieces. I don't need to distribute to pieces here because, of course, this 1/2 is already doing that. And so by multiplying the 2 times the 1/2 and having them cancel, we end up with just the absolute value on that side. So that gives us the absolute value of 6 minus 2x. And that will be equal to 6x plus 2. Now, this gets a little bit tricky because when it was just a single number over on the right side, it was easy to see that what could go in the middle here was just the positive or negative of whatever the number was. But now we have this entire thing on the other side. We need to treat all of that as a single number, and what can go on the inside here is either the positive or negative of this number. So therefore, my two possible solutions are going to be either what's inside the absolute value, 6 minus 2x, could be equal to just the number that we were given, 6x plus 2. Or the other possibility is that 6 minus 2x could be equal to the negative of 6x plus 2. And then I want to solve each of these equations. So on this first one, I'll subtract 6x from both sides, while at the same time subtracting 6. So that causes canceling here and here, providing negative 8x is equal to negative 4, and then dividing both sides by negative 8. Leaves me with x equals 1/2 when I simplify. On the other side, when I distribute the negative on the right, I'll have 6 minus 2x equals negative 6x minus 2. So notice that both the signs of both pieces get changed. In this case, I'll be adding 6x to both sides and subtracting 6. Causing canceling here and here again. And so in this case, I'll have a positive 4x equals a negative 8. Or dividing by 4 on both sides, I'll find x equals negative 2. So those are my two possible solutions. Now I need to check both of them. So go ahead and check both of them back into your original equation. And I will tell you this, both of these are not going to work. Only one of these is going to work back into this equation. So check carefully, and then after you finish checking, only put the solution that works back in the solution set. All right, so go ahead and pause the video and do that right now. So assumably at this point you have found that one of the solutions works and one doesn't. And so therefore, at the end, make sure that you make your solution set with the one that worked, and the other one you're just going to leave off or neglect because it's an extraneous solution. All right, let's move on to the next topic. Now we can also have absolute value inequalities, and these work a little bit differently. An absolute value inequality can be represented or expressed by either an and or an or compound inequality. So thinking back to our last section where we talked about inequalities, we're going to end up with a compound inequality. There's going to be two parts to it, just like there's two parts to the equation. So let's take a look at this example. If I have the absolute value of x is less than 3, let's remember what the absolute value of x means. It means the distance of x, which is what we're looking for, away from 0, right? So here it says the distance of x is less than 3 away from 0. So if I looked at my number line, the places that I would be allowed to be, well, here's my origin right here at 0. And then anything like 1 or 2 or 1.5 or 0.5, and even these negative numbers, these are all a distance of less than 3 because here's a distance of 3, and there's a distance of 3. And we're saying we want the distance to be less than 3. Therefore, we're going to include everything between negative 3 and positive 3. But we're not going to include 3 because that distance is less than 3, not less than or equal to 3. So that right there shows our inequality. Now, if we were to express this as a compound inequality, this would be the same as negative 3 is less than x, while x is also less than 3. Or I can say x falls between negative 3 and 3. Another way I could write this, obviously, as an and inequality would be that x is greater than negative 3 and x is less than 3. This is the exact same thing as what we have up here. It's just written in a different form. All right, now let's take a look at another example. If I had the absolute value of x is greater than 2. So again, I'm going to number my number line from negative 3 to 3. In this case, though, it's saying the distance of my solution, which is x, the distance needs to be greater than 2 away from our origin. So that means that I can't do any of the stuff that's in here because this is all within 2 units of the origin. Instead, I'm going to shade everything that is more than 2 this way, so everything from 2 up, and also everything that is more than 2 away from the origin down here, which is negative 2 and down. Of course, in this case, because it was greater than but not equal to, I'll do an open circle there and an open circle here, not including those points. And we can see now that this is simply the inequality. X is less than negative 2, or x is greater than positive 2. All right? So those are our two pieces. Now, something interesting about each of these pieces, you'll notice it's sort of similar to what we did with the equations, breaking into the two pieces. The difference is that for the negative value, notice what happened to the sign. The sign flipped, right? It was a less than, it became a greater than for the negative value. Over here, it was a greater than, but it flipped to a less than for the negative value. And in all cases, if it's a less than, then it becomes an and inequality. And if it's a greater than here, it becomes an or inequality. So let's go ahead and write our method. Our first step is to isolate the absolute value on one side of the inequality, very similar to our first step with equations. So get the absolute value all by itself. Our second step will be to write the compound inequality. And remember that greater than or equal to means it's going to be an or inequality, and less than or less than or equal to means it's going to be an and inequality. For either case, though, we know that the sign will flip, the inequality symbol will flip. So it flips for the negative solution, right? So don't forget to flip that inequality symbol. Our next step then is to solve each inequality for the variable. Then we can graph the solution on a number line. And finally, we can express our solution using our interval notation that we learned in the previous section. All right, so here are steps for solving absolute value inequalities. So looking at this next one, it says solve the inequality, then graph the solution set and write the solution in interval notation. And we have the absolute value of 3x minus 12 plus 4 is greater than or equal to 10. So our first step here will be to subtract 4 from both sides in order to isolate the absolute value. And that'll give me 3x, absolute value of 3x minus 12 is greater than or equal to 6. Now, because it's a greater than or equal to, that's meaning that the distance, my absolute value, the distance is greater than some number. And so that's going to mean it's an OR inequality. So my two possibilities will either be 3x minus 12 will be greater than or equal to 6, or 3x minus 12. Now for my negative solution, I know that I need to flip the sign. It will be less than or equal to negative 6. Working my first one down, when I add 12 to both sides, I'll have 3x is greater than or equal to 18. And then dividing by 3, we'll find x is greater than or equal to 6. So there's one half of it. The other half is going to be, again, adding 12 to both sides. And so that will provide 3x is greater than less than or equal to positive 6, because when I add 12 to the negative 6, I get positive 6. And then x is less than or equal to 2 when I divide both sides by 3. This is still an OR inequality. So now I'm ready to come over to my number line, and I see that it needs to go from at least from 2 all the way up to 6. So putting numbers on my number line, here I have the numbers from 1 to 7. And let's graph each piece now. Now remember, OR inequalities, when we think about this is like your parents saying you could do this or do that, and either one will get you to where you need to be. So if that means I take all the solutions from both pieces. So x is greater than or equal to 6. Because it's greater than or equal to, it's going to be a closed dot, and greater than goes in this direction up my number line, filling in the arrow at the end. At the same time, it says, or I could have x being less than or equal to 2. So that means that it could be 2, or it could be anything less than 2. So I'll shade going down my number line in this direction. So that's the graph of my solution set. And now I want to do my interval notation. And my interval notation is simply going to be starting with the left-hand piece here, because I can't put a dot on negative infinity. It's parenthesis, negative infinity, comma, 2. And because I'm including 2, I put a square bracket on it. And then starting it down the other piece, I'm going to have a square bracket at 6, because I'm including 6. And then I'm heading up towards positive infinity, and I can't put a dot on that, so it's going to have a parenthesis. And then because these are both part of the same solution set, I'll put a U to show that it's the union of both of them that represents my entire solution set. All right, so that is my solution. There is no check here because the check is actually the graphing. If it found that when I tried to graph that I found no overlap, that would be no solution. But we're going to actually, that would only happen if we don't catch the signals as to what is possible. So let's take a look at some additional problems. So on this one, again, we want to start by isolating the absolute value. And I can do that by dividing negative 5 on both sides. And that will give me the absolute value of 2y minus 2 is greater than, that should be is less than 3. Because remember, again, anytime I have an inequality, if I divide by a negative, it causes my inequality symbol to flip. So really important that we're keeping our eye out for that. All right, now I'm ready to break it into the two possible inequalities. Because it's a less than, I know it's going to be an and. And so therefore, the two parts of my inequality will be that 2y minus 2 is less than 3. And at the same time, I also have to go by the restriction that 2y minus 2 will be greater than negative 3. The other way to write this, of course, would be 2y minus 2 in the middle, and that's going to be greater than negative 3 and less than 3. So you could do it either way, whichever you prefer. I'm going to go with the first method, though, just to work it down. So adding 2 to both sides will give 2y is less than 5, because I added 2 to both sides, and then dividing by 2, y will be less than 5/2, which is the same as 2.5. On my other side here, adding 2 to both sides, and I'll have 2y is greater than -1. Dividing both sides by 2 will give me y is greater than -1/2. Notice that the sign didn't flip because I didn't divide by a negative, right? I divided by a positive. So I can do my number line now. So I'll number my number line here from -2 up to 3. And then I want to graph each of these halves. Now again, remember this is an and inequality, which means that I need to go by both pieces at the same time. So y has to be less than 5/2. So on my number line, 5/2 is going to be halfway between 2 and 3. Less than means I don't include it, and then it's less than, so it goes down in this direction. I don't know how far yet, because I still need to look at my other one, which is y is greater than -1/2. -1/2 is here. Again, I don't include it, and greater than goes in this direction. So I can see that the place that I'm going to shade then is simply going to be between these two restrictions. I can't go any further this way because it wouldn't meet this restriction, and I can't go further this way because it wouldn't meet this restriction. So this represents my graph, and now I'm ready to do my interval notation. Because my starting point is here at -1/2, but it's not including it, I'll do a parenthesis, and then -1/2. And then I want to go to the ending of this part of the solution, which is right here at 2.5 or 5/2, again, not including it. And because there was only one area of solution set in here, there's only going to be one piece here. Okay? That's different from on our last page, where we had 2 different parts of our solution set, and therefore we needed 2 different pieces to indicate each section. So that is our final solution. We have our graph and our interval notation for our solved absolute value. Let's take a quick look at these next 2. For this next one, I have 7n plus 4 is greater than 0. And so, of course, I always start by isolating my absolute value, so I subtract 4 from both pieces. I'm going to write it over here. That would give me the absolute value of 7n is greater than -4. Now, remember, we have a negative that's being equated to or being compared to an absolute value. That should give us some pause. So let's think about this. Absolute value we know is always positive. So therefore these numbers over here will always end up being positive no matter what value I choose for n. And of course a positive will always be greater than -4, right? And so therefore, even without solving this out, I'm going to see that this will always be true. Because of this, I can go ahead and number my number line, but because it's always true, there's no value of n that doesn't work, and therefore, when I shade, I get to shade the entire number line and then fill in both ends. So that means that all numbers on my number line work, and the way to indicate that with a solution set, there's 2 ways. I can use all real numbers. This is what I would use in place of a solution set, right? Set builder notation. Or if I want to use interval notation, I'm obviously going from -infinity here on one end all the way to +infinity on the other end. So all 3 of these, the capital R with the double line there, the number line, and then my interval notation down here indicate that all numbers will work in this particular inequality. Looking at this next example, number 8, again I'm going to start by isolating my absolute value, and so here, because of the negative on the outside, I'm going to divide both sides by -1. That'll give me the absolute value of 2w plus 3. Now, because I divided by a negative, my sign flips is going to be less than or equal to -15. Now, this would normally be an and inequality, And I could go ahead and break it up and solve it like that, but I can actually shortcut this method a little bit by recognizing that no matter what I put in place of here, I can never have an absolute value that'll be less than a negative number, because it'll always be positive. Therefore, I can see pretty quickly that there is no logical solution to this, and so this is going to be simply, as we saw before, an empty set. On my number line, therefore, I would simply leave it blank. There are no solutions to put on there at all. Now, if you were to work either of these, 7 or 8, if you were actually to work them out, because this first one here is an OR inequality because it's greater than, what you'd find is that after you solved it down, you would have a piece that went this way and another piece that went this way, and because they overlapped and we take all the solutions, that's why we end up shading the entire thing. For the AND inequality over here, because it's less than, we'd find that we'd have a solution going this way and a solution going this way with no overlap, and that's why there's no solution. So we could have two possibilities here when we are setting an inequality, an absolute value inequality, comparing it to be greater than or less than a negative. Either we're going to have all real solutions or no solutions. Alright folks, that's it for this video. We'll do the last couple puzzles in a different video or in class. So I'll see you in class tomorrow.